Okay, I represent an enough LSST team, including Barbara, Maribel, Filippo, Chiara, and myself. We are all members of the Transients and Variable Star Science Collaboration, and we are presenting a Blazars science case for LSST. So what are Blazars? Blazars are active galactic nuclei with a jet pointing towards us, so that the emission from the jet is relativistically being, the flux is enhanced, the variability timescales are shortened because of time contraction, and the frequencies are blue shift. Blazars emit at all wavelengths, and the emission is variable in an unpredictable way, and the time scales range from minutes to years. There are different types of blazars. Based on the presence or absence of emission lines in their spectra, we can distinguish between flat spectrum radio quasars and BLAC objects. Then we can further divide BLACs into low energy peak BLACs and high energy peak BLACs, depending on the shape of the spectral energy distribution, which is this plot here in the usual log nu F nu versus log nu plot. You see that the spectral energy distribution has two bumps. The low energy bump is synchrotron radiation in the jet, and in inverse Compton bump is probably, likely, inverse Compton radiation. And you see the difference between low energy peak BLACs with peak at lower frequencies and high energy peak BLACs. The spectral energy distribution is dominated by the non-thermal polarized radiation from the jet, which is very variable, but in the optical, the situation can be more complex because we can have contributions also from the accretion disk and broadline region, which is less variable, and from the host galaxy, which doesn't vary at all. So in case the accretion disk and host galaxy contributions dominate, it is very difficult to distinguish a blazar without spectroscopic or multi-wavelength information. These are two examples of flat spectrum radio quasars. On the left, you have an object whose optical emission is jet-dominated, while on the right, we have an object whose optical emission is dominated by the accretion disk. Notice the high Compton dominance, that is the strong, the powerful emission in the gamma rays. And here are two examples of BLAC objects. On the left, low energy peak BLAC, jet dominated in the optical, and on the right, a high energy peak BLAC, whose optical emission is dominated by the host galaxy. And notice in this case, the peak of the inverse Compton emission in the TeV band. Blazars are few. If you look at the two main catalogs, you end up with less than 5,000 objects. Most of them are faint. We are expecting that LSST will discover a lot of other faint objects. But they are very important because by studying jet emission, blazars emission, we are seeing what is happening inside the jet, in the inner parts of the jet, close to the supermassive black hole. And we have a kind of biased knowledge of blazars because we know fairly well the brightest and most variable objects. And for these objects, we can organize multi-wavelength campaigns as we do in the framework of the Whole Earth Blazar Telescope that we are leading from Torino. And we got nicely sample Likers, even in intraday timescales. We can follow also the polarized behavior. We can have a lot of multi-wavelength data, and we can give nice interpretation of what is happening. But we lack deep knowledge of the vast majority of the population. Another interesting thing is that blazars are powerful cosmic accelerators. In the blazar jets, photons are accelerated up to gamma ray energies, and in fact, blazars are the most abundant populations at gamma rays. But blazar jets also accelerate particles, and they are expected to produce neutrinos and cosmic rays. And last year, we had the first strong association of a high-energy neutrino detected by IceCube, the IceCube Observatory, with a flaring blazar, the object TXS 0506. So, blazar may really be the birthplace of the most energetic particles in the universe. And now to the white papers. We know that currently LSST will perform 2 visits per night in the same filter, and then again another visit, not necessarily on this. I see, Federica, you are saying maybe not, but I mean, okay. Okay, for blazar styles, 3-4 days sampling would be not bad, unless the object is flaring. In that case, we would like to have a better sampling. But the problem is that we need a reference filter because our objects undergo spectral variability. So we really would like to follow them without introducing errors because of color changes. Another big problem is saturation, because now one visit is thought as 2 snaps of 15 seconds, but the saturation limit at 15 seconds is already 16, which is quite a lot. So we were thinking of proposing 2 snaps with different exposure times, for instance 2 plus 28. But we were warned that LST will provide photometry of the 2 snaps combined. So having a shorter snap would probably require a lot of user work in order to get photometry only on the short exposure. But then, is it possible to correct for saturation? Well, in principle, yes. And methods have been developed to solve the problem, for instance, for the Kepler K2 data. But we are not aware of, let's say, official documents on how LSST is handling the problem. Another thing is that we heard about twilight proposals for bright objects, so maybe this is something that we should consider. Last slide. Deep drilling fields. We were wondering whether to propose a deep drilling field point on the neutrino science case. So if you look at this map here, okay, the blue plus signs indicate the neutrino source candidates. There will be 4 of them in the main survey, and 1 TXS in the north ecliptic spur. So the question is it reasonable to propose a deep field pointing on this object with short exposure? Otherwise, it will saturate. And the field would look like this, and it would contain other 4 blazars, so it would be a nice field for blazar studies. Or should we rather ask for short exposure in the North Eclipse per mini-survey? Or should we ask for several deep drilling fields on the best neutrino source candidates? Or finally, could it be a target of opportunity proposal to check this association between high-energy neutrinos and blazars? Well, I'm sorry, I have too many questions. I hope to find some answers during this meeting. Thank you very much.
Thank you, Claudia. Questions for Claudia, comments for Claudia?
Thank you. Just to clarify while I was shaking my head, that's not necessarily written in stone that the filters have to be the same for the two visits. That will definitely happen over the same night within a 30 minutes or so window, 2-hour window for the solar system science. However, there is a compelling argument by the solar system science collaboration to actually do that in the same filter because their throughput depends on the sensitivity of the shallowest filter of the pair. But you know, if they're in filters that reflect sunlight, there is not a really, really compelling requirement to keep the same filter, as long as you don't go to U or Z. And then I recommend you take a good look at the gap, the intra-night gap for when the next visit is, because for different surveys it varies by a lot. And even the median gap, you know, the distribution of intra-night gaps can be very significantly broad. For the same filter, a lot of the simulations that have been produced have 2 weeks return time to the same field or so. So not quite 3 days. 3 days in a different filter, but even that has a large spread.
Okay.
The idea of changing around the snaps to have different times between the two is really cool, and I'm kind of interested to hear more about that. But I have a more naive question, which is just, how do you observationally distinguish blazars from ordinary quasars?
Yeah, we are working on this.
Okay.
For some sources, it's straightforward. It's just you look at the variability, if they are expected to be more variable than ordinary quasars. But as I was saying, there are objects in which the accretion disk dominates, and these are quasars. So if you don't have multi-wavelength information, it's very hard.
So it's the amplitude is that the main factor?
Pardon?
The amplitude of the variation is high?
We have so many different situations, so
Okay.
It's difficult to say.
So how attached are you to that 2 seconds for the two different times? What is a, like, 2 seconds is really, really short. The noise will be horrifying. And right. Right, but so if we if we wanted to realistically recommend something that is not as extreme but still useful for Blazar, what is really your hard limit where things are no longer useful?
Sorry, Claudia, I have a curiosity. What is the fraction of objects that you already know where they are, compared with the unknowns? So after the 500,000 AGN found by Gaia, and probably another similar fraction that is coming the next year, do you have a solid idea where the most interesting objects are already distributed, or is still something that you are looking for new possible targets? Okay, because otherwise with the 2-meter telescope you can follow all of them. 16 magnitude is something that you can do with VST almost with peanuts, if you know where they are.